Hold on. Are you able to see my screen? Hold on.
Yes.
You can still see the problem? Can y'all still see the problem?
Yeah, I can see it.
Say it again. Oh, it's the same link. Underneath the original physics one, look in the announcements. It should be the same one. I made it to where it's like recurrent, so it never changes. So you just always use that one. All right. First problem is the Michael Jordan problem. Yes. All right. So from day one, right, we've been talking about this Michael Jordan problem. The first way we learned it, right? If I gave you a sheet back, I want you to write on your sheet so you can have it and use it as notes. If you don't have a sheet, just take out a blank piece of paper and just write down at the same time. Now, when we started talking, right, about kinematics, we had these different sets of equations, right? Remember what some of them started off with? We had the first one being something related to average, let's say just speed, right? That is ended up being our change of position over time, right? But what change of position? Our distance, because we do scalars go together, right? Distance. Now, what is having our distance over time? That's our first definitional equation. Then we go to our second one. We start looking at the average velocity. We're looking at a vector. It's still position changing over time, right? But this time it's displacement. See how I put the little hat for the vector? Then we got to our last definitional equation. So we're now the last definitional equation represents acceleration. Still over time, but we're looking at the change in our velocity. Change of our velocity over time. These, once again, are definitional equations. They define the quantities that we learned when we looked at the stat graphs. Now, we did some manipulation, playing around with some stuff. I added the bonus equations that we had, right? We got change of velocity equals the final velocity minus the initial velocity. Then we also have average velocity is equal to, when we're talking about situations of constant acceleration, which is all the problems of 1QD kinematics, we have the average velocity is equal to the initial velocity and the final velocity divided by 2. These are all important, right? Because these lead us to now what we have being kinematic equations. So if you see on your paper, right, and I say use kinematic equations, right, and I might write the equation on there, it's because can we find the answer using definitional equations? I think you actually did the first one using definitional equations. Yes, but you did this.
Yeah.
And it took a couple extra steps, right? And those steps you have to remember, right? Why we use kinematic equations is because it's almost like I would say like a one size fits all type of formula to where now we can put different quantities in there without having to do this manipulation from the definitions. We do it in the big beforehand to get these different equations so that way when we have a situation we want to represent motion, we're just plugging in numbers. But it does require us to know which one we're going to use for which situation, right? So let's just go through it real quick. So then we have our first one. I'm not going to derive them because they're in the slides just so we can just move through, but I want you to review them so you can see it again. The first one looks at us talking about how do we find the average velocity. Now this is you making your cheat sheet so that you can remember this stuff and be able to come back to it. So how do we describe average velocity? Sorry, a final velocity. The final velocity is also known to be equal to the initial velocity plus the acceleration times delta t. That comes from this right here and using this change of velocity. We do a little bit of algebra manipulation to where now we know if we have the initial velocity and acceleration in the time we can find the final velocity. So if I don't know one of these, but I have the other three, I can use this equation. Now we go to the next one, right? The next one still talks about distance, displacement. Let's just do displacement equals the average velocity all times time. But how can we represent the average velocity? We can substitute it as the final velocity plus the initial velocity divided by 2, just taking this right here. So now we can say this here plus this here over 2. And then if we multiply that by time, we can find our obvious displacement, right? We can find displacement. Now these two, right? These two start us off, but these two lead to the next ones that we have, right? So where we really start to get to play around and really get the typical kinematic equations. Like this third one is the one you're going to see all the time on this paper. This starts to help us represent free fall motion, right? If I want to find my distance or my displacement, right? How much I change my position, it's equal to the initial velocity times the change in time plus 1/2 acceleration times the change in time squared. Now, this right here comes from combining these two together and doing some manipulation, right? But this is one of the equations that we use the most for kinematic equations. This one right here. You're going to see this on your paper a lot. Now, what we need to do is let me do one more, right? I have another one to find the final velocity. So the final velocity being the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position or displacement or distance. That's the last one. This is the D. These are our 4 kinematic equations. So now, when we go back to these problems on this practice exam, we did all the hard work of deriving these so that we can actually use them. These are all in the slides, and I showed you how you use these to get these. But the purpose of doing that is to use these on these short problems. And how we go about them is we have to find 3 things when we're doing our problems, right? So when we're problem solving, in each problem, there's going to be given information. They're going to give you something, right? Then there's going to be some type of assumptions. These assumptions comes from the rules that we talk about and we describe, right? Like an assumption, right? What's always present?
Right.
Gravity. That's an assumption, but we know that, right? We're assuming that gravity is always present, but we know that to be true. Just like how when in 1D kinematics, We're assuming that acceleration is constant. That's what we're doing. Now in 3, right? You have your giving your assumption, but we also have to find what are we solving. That's what we call as the unknown. What is the unknown that we're trying to find? In doing problem solving, you want to find these 3 things and actually label them. Like if you write on your paper, what is my given? What am I assuming? And then what am I trying to find? It will literally give you exactly which one of these equations to use. Not this one, because you got to do a lot of manipulation with over here. You don't want to spend too much time on that because also you're widening your brain to go ahead and make more mistakes. Come over here. But start with these 3, right? Now let's attack that with the Michael Jordan problem, right? So if I read this first problem, and it's also on the screen as well too. Michael Jordan was said to have a hang time of 3 seconds, at least according to a popular Nike commercial. Use, this also too, we got to read, use kinematic equations to determine the height to which Michael Jordan could leap if he was wearing Nike shoes and had a hang time of 3 seconds. They said the same thing twice. So they only gave you really one piece of information. All the rest is fluff. Now, let's go and for the Michael Jordan problem. I don't even need much space, right? First, just so we see the parallel. My given is what? What did they give me? Say it louder. 3 seconds. So I have 3 seconds, right? Now, let's set the scene. Michael Jordan's doing what? What is he doing? Jumping. So he's in the air. When you're in the air, you're doing what? Similar to F word. Falling, because you're in the air, you're flying, right? You're trying to fly, you're defying what? Say it louder. Gravity. Gravity is always present, right? Is that an assumption? I just gave the answer, but yes, that's an assumption. So we got an assumption that gravity is present, right? We assume there is gravity, right? If we assume there's gravity, gravity has a value. Do we know what that value is? Say it louder. 9.8 what?
9.8.
For what?
Second.
Per what?
Square.
Yes, per second, or per second squared. Now, what does this mean? Meters per second squared. It's the units for what type of quantity? Acceleration. So now, not only are we assuming that gravity is present, we actually have an acceleration. So we have an acceleration, right? Now, for the third thing, right? What is the unknown? What are we trying to find? Now, this comes back to reading the problem. The height. What is a what? A what? Distance, displacement, a position, right? So now we need to find the height, or let's just say D, the change in position, distance, displacement, which one doesn't matter right now. But we need to find this, right? What is this? Now, this is also a time. Now that I put it out and spelled it out here of the quantities, what 2 quantities do we have?
The time, acceleration, and distance.
Time, acceleration, and do we have distance?
Oh, no.
We're trying to find it, right? Now let's look. We have time, acceleration, and we're trying to find distance. I know which one I'm going to use, but do you know which one you would try and use?
Yeah.
Which one would you use to find the distance? And you have time, acceleration so far. You have time and acceleration. 3. So we're going to use 3 right here. Now, in 3, I count how many different variables? 4. How many do we have right here? 2 that we know and 1 that is unknown. Now, when we are solving a system of equations, can you solve a system of equations alone with two unknowns? No. So we need to, in 3, if we want to use it, we need to find out one more quantity. Now, let's think about it, right? We were only given 3 seconds. We have an unknown, right? We assume that gravity is present, so now we have an acceleration. Out of these quantities right here, we know we need to find what's the only quantity that's left that we don't know? Initial velocity, right? Now, can we make some type of educated guess or assumption about what the initial velocity would be?
0.
0, 0. Now, can you give me an explanation why we're saying the initial velocity is 0?
Because you have to be completely stopped in order to jump.
You have to be completely stopped in order to jump because you got to at least do a lift off. You got to start on the ground before you can leave the ground. So when he starts on the ground, he has no velocity. Does that make logical sense in just jumping? Just motion? So if it does, we can actually assume that the initial velocity is going to be 0. So now we have another assumption. So now we can assume also that the initial velocity is equal to 0. 0 what? Say it louder. Meters per second. Make sure we keep the units because the units help you figure out what's going on. So now we have 1, 2, 3 quantities that are known, and we have 1 unknown. Now can we solve this equation to find out the unknown? So now this is the easy part. All we do is take this equation, transfer it down here, but with actual numbers. I'm going to put the numbers in blue. Let me rewrite it first, so then you can see how I actually put everything in here. You should do this the same way. You wrote your given, your assumptions, and you have your unknown. Now you're going to rewrite the equation. If you wanted to, on the side of your paper, write all of them out and then literally box in which one you're using for that problem. That can also work. Or you could just jump right to here. If you had a cheat sheet, just go and start here. But always start writing the first equation. So now I'm going to say yes.
In time of 3 seconds, we divided by
We're getting there. Yes. So now we're here. We're going here. Let me start substituting values. But since Victory just said it, right? The first value, I have my initial velocity, which is what? 0. So I'm going to put a 0 here. I'm going to still put the units, so we know we're talking about that. Now, Victory just said it, right? The time, the given time is how much?
3 seconds.
3 seconds, right? But like she just said, with hang time, right? Hang time would be what? The total. Describe hang time in your own words.
Time up plus time down.
Time up plus time down, right? Time up plus time down. Do we want to, when do we want to measure his greatest height?
All the way in the air.
When he's all the way in the air. When does that happen? Where he's in the parabola, but what part of the parabola?
Half the middle.
Half, the middle. The part where he goes like this, the whole motion looks like this, right? But we want to get to him where he's at the middle. So now, if we're going to the point where he's at the middle, what does that do to our time? Cut it in half, just like Victory just said. So now, this given, we could even write it as another assumption, right? Assume that max height is at half time. For this case, that's 3 divided by 2 is what? Huh? 1.5. So we can assume at this time of max height is going to be at 1.5. What does that do to our problem? When we come back up here, instead of us putting t is equal to 3, we're going to put t is, say it louder, 1.5. And we go carry it over here too as well, right? 1.5. We already established that gravity is present, and gravity is our what? Say it louder.
Acceleration.
Acceleration. So now I'm gonna put 9.8 meters per second squared here, and we just established our time was 1.5 seconds, and we're gonna square that. Now, physics. Everything in green is physics. That's physics. This right here is math. Once you get here, you technically have the right answer already. Because if you make a mistake here, you made a mistake with algebra. But to be honest with you, in this society, everybody has a calculator either on their phone or their computer. You could literally take a screenshot of this and it will give you an answer back. This is the final part where you just plug in the calculator. But you have to get here by setting it up the right way, and this is mostly just logic. Once you get here, plug it in or just solve it yourself. This is going to be 11 and some change. This ends up being 0. 1/2 of this is 4.9. 1/2, 1.5 squared, I believe, is what? 2.25, something like that. And then you multiply that by 4.9, and you get 11.025. Yes, I was able to do that math very quickly. I've done this problem a lot. I'm also pretty good at math. But you don't even have to get that far. You could literally just plug this in or take a picture of it. Or even if sometimes, some cases, some people might actually let you just leave this right here because they can figure that out. And that's fine. But we have to get to understanding this. And this really is not that hard if you take your time and you walk through it. You got to really get comfortable with speaking to yourself, talking yourself into the answer. But this is the solution to number 1. To be honest with you, the real work is 3 lines. If you would have just did 1, 2, 3, you get full credit. And how I graded it is this, right? Now I'm being very nice too, because I need you to be comfortable putting something on the paper. Putting something on the paper, anything, literally just writing a random number gets you 1 point. Because you gave me something. You attempted it. You tried to show your work. That's what I need that. Now getting the correct answer gives you the other point. That's why I made it out of 2. So typically, if you would have just wrote this answer, the original equation, I would have gave you a point because technically you are giving me something, which is a kinematic equation. Now, if you solve it, which is these next 2 lines, you get the right answer. We'll get you 2 points. And that adds up over time. Let's go to the next one. Because that one was like a practice one. We went over that problem so many times, right? Very much went over a lot, right? Now, these problems I took out of a textbook, and this is a calculus-based textbook, but these are not calculus problems. These are still the same type of algebraic problems that we have, but the wording might be a little bit different, and it might be a little bit more confusing. But it's still in the same vicinity, right? A kinesiologist studies the biomechanics of the human body. She determines the velocity of an experimental subject while he runs along a straight line at a constant rate. The kinesiologist stops the stopwatch at the moment the runner passes a given point and stops it after the runner has passed another 20 meters away. The time interval indicated on the stopwatch is 4 seconds. They said a lot, but we have useful information, right? What is given? I'm going to erase this. Just real quick. What is our given? Time. We have a time. I'm going to just write the quantity, right? We have a time. What else do we have?
20 meters.
We have a distance. Time was how long? 4 seconds. Distance is how long?
20 meters.
20 meters. Now, here's something that we can assume. We can assume, right, from what was given to us. What else thing did they tell us that they're given? But it's not as a number, but it's just about the type of motion. It's what? Say it louder. Moving at a constant rate. That was also given to us, right? Constant rate. Now, what do we know about constant rates when it comes to quantities, right? If the rate that my position is changing, which is also my velocity, is constant, what else do we assume? Or can we conclude from that? If the rate at which my position is changing, my velocity is constant, what else do we know? Say it louder. There is no acceleration. Therefore, my acceleration is equal to.
Wait, did you say that one more time?
The rate at which my position is changing, or my velocity, tells me that my acceleration is 0 because there is no change in my velocity, because acceleration is equal to the change in over time. So now we know acceleration is equal to 0. And what is the unknown thing that we're trying to find in the first problem? The velocity. We want to find the velocity. We want to find the velocity. Now, to be honest with you, there's a multitude of ones that we can use. But this one right here, which one would you use for kinematic equations? If we have distance, time, we know acceleration is 0, and we want to find velocity, which one would I use?
The distance over time,
Which one?
the velocity. So
So you're going to use this one.
Are you talking
D
about the
equals D
definition?
over T.
So you're going to use that one. Yes, that is a definitional equation. Typically, this would be good to use a definitional equation. But which one of the kinematic equations could you use?
First
I
one.
didn't use the kinematic. Oh,
As I'm saying, yes, you don't know. You could use the first one to find the final velocity, right? Let's think about it, right? Or you can find one of these velocities. We know this is going to be 0. We don't have a time.
I guess you can.
Okay, so you can't use this one because we're missing one. Let's go down. Can we use the second one? Because we don't have what?
Velocity.
We don't have the velocity. But think about it, right? What will we find? Let's say, what does this represent? Say it again.
Oh, that just turns into the D.
Exactly, which turns into this, right? Because this technically is what? Average velocity, right? So now we can at least just know the average velocity, but is that not what we're looking for? What is the runner's velocity? Just through that moment. We just want to find the average. We don't need the instantaneous, the initial, final. We just need the average of that whole time. So really, we could take this and do the same thing as making it over here, right? So let me just convert this over here, right? Now, this is the physics side, right? Using the definitional equation for this one would have been fine. But let's say if I do this, right? This is just if I had kinematic equations. I know that this is average velocity, so I could just change this to average velocity times delta t equals distance or displacement. Distance. It doesn't matter right now for distance, right? It's fine. What was the distance that we had? So I could put 20 meters here. I'm gonna put it in blue. Actually, I'll put it in green. So I made this blue. 20 meters. And did I have a time? Did we have a time?
4 seconds.
4 seconds, right? So I'm gonna put that over here, 4 seconds. And we want to find this velocity. Now, let's go back to seventh grade. I see, do. I see multiplication by 4. So I do division by 4. So I divide each side by 4. So that I should have a velocity, right? And here's the key thing, right? It's 4 what? 4 seconds, right? So I'm dividing 20 meters by 4. So when I do this, right, I'm going to get 20 divided by 4, which is 5. But look at my units. My units are now meters over
Meters per second.
meters per second, because it's meters over second, because I just divided it. What's the typical units for velocity? Meters per second. So now you know you did it right because you got the same units. The units are important because they help you figure out, am I dividing this right? Am I getting the right quantity? So now you got 5 meters per second equals the velocity. This still, all of this is physics. This last part was math. Physics, math. That's the second one. So we got the first part, we got 5 meters per second, 5 meters per second, right? Some of your papers, I might have told you to use the definitional equation, right? So when we get to this next one, and we ask, now, right, we have the velocity, right? And so now we're asking if the runner continues with this motion, right? After the stopwatch is stopped, right? So like after the stopwatch is stopped, right? We know what that velocity is. What is the person's position after 10 seconds has passed? Let's go back to the problem, right? We have we're given a what? With part B, they gave us a what? Which is how much? So now let me change this 4 to a 10. What else did they give us? What else did they give us?
Well, it's the same velocity.
Wait, hold on. What is that?
Constant velocity.
How do you know it's the same velocity?
Continues his motion.
So because they told you he continues his motion, you did what? You assume we have the same velocity. So now that's an assumption that our velocity is still going to be 5 meters per second. But that assumption makes sense because they said what?
He continues his motion.
He continues his motion, and his motion was what? Constant, which therefore means the velocity is constant. And when we have constant velocity, do we have
No acceleration.
no acceleration? So acceleration is still equal to 0. And we're trying to find what this time now?
We want distance.
Distance, because we're looking for that person's position, right? So let's do distance. So now we're looking for distance. Now, what equation will we use?
I don't know, but I know.
Look,
Whatever.
look, look.
Oh,
look.
this first one, distance over time.
Yes, the same thing. Or we could just go back to what we just did, but we just plug in different numbers. Because look, it's the same thing. Now we have a distance and we have a we have a velocity and we have a time. And we want to find a distance. So I could literally just erase this. This is me being lazy. Yes, I'm not going to rewrite the whole thing. And now this is my unknown. My velocity is what?
It's 5 meters per second.
So now I just put 5 in right here. And my time is what?
10 seconds.
10. So then 5 times 10 gives me my what?
Meters.
50, which is my what?
Your distance.
My distance, right? Or my position at that time, right? So now I'm at 50 meters. Now, the thing is, right? Some of you put on there 70 meters because I see what you're doing. 20 meters has passed and you go 50 on top of that. No. From the time that the stopwatch is stopped, that's when we start. From the time that the stopwatch starts, that's when we start looking at this motion. Which means that when the stopwatch is stopped, we are initializing that to be our 0. That's our start. So that time the stopwatch is stopped, we don't care that he's already went 20 meters or whatever. We say that that's our 0, and then what is our position after that? So when the stopwatch is stopped, we are at 0. So that's like this. This is 0. And then after the motion, we measure again. And what is this position right here? From what we just calculated, that is 50. Even though earlier in the problem, they said that this motion was 20 meters. We're only focused on this part right here to here. Does that make sense?
Yeah, I think so.
Okay. Good.
So you're basically saying if it's somebody, to say for instance, you start right there, if I have a stopwatch and you start right there, and then I stop the stopwatch right there at the table, that's when it actually starts.
Because that's the constant velocity that we're looking at when it stopped, when you stopped it again.
Okay,
Because
so-
we found that velocity from the previous problem.
Which is 4 seconds. Okay. However many seconds. Okay, 5 seconds.
5 meters per
Second.
second. That's the velocity. Yes, that motion was for 5 seconds. You go in there. But now that we did that, we're going to keep that speed and carry it for another 10 seconds.
Okay.
And then we want to see where we're at. And from this point of when that stopwatch was stopped, that became our new 0. In 10 seconds, we went 50 meters because we held a constant velocity of 5 meters per second. Are you good back there? Because your face is confused.
Yeah, I'm good. But 70 meters away from the start is not incorrect. It's just not what you were asking.
No, it's one of those problems where we could get into being ambiguous, right? I don't want it to be ambiguous. For this one right here, I'm saying it's 50 because we're measuring our new 0 from when the stopwatch is stopped. So we're caring about the motion from when the stopwatch is stopped, let's say the second time. So I pressed it to get my speed, right? Because I needed a time to get my speed, right? So I pressed it, see how long it took for me to go 20 meters. That's this right here. It took me 4 seconds to go 20 meters. Now, I'm maintaining that same velocity for another 10 seconds. Where is my position? But from when I stopped it the second time, this is now a new 0. We don't care about for the previous time that we went, right? So instead of saying this is 20 meters, we're worried about me at the edge of the table where it's now 0. Now from 0 to 10 seconds, how far did I go? 50 meters. That makes sense? And I think that happened a lot with a lot of these problems. So where it would get confusing because there's a couple where you could be, I debate it and you'll see like some of you put down like a different answer. Like some of you put down like another one, like 70 or something like that before. And I said, okay, because when I read the question, it can be a little confusing. So let's go to the next one, right? I am hitting all of these, but I think this is probably very valuable. We'll still stop at 7, right? Actually, let me ask, is this good, like going through like this or?
Yeah.
Okay. Now, same thing, right? These questions really not that hard. You gotta really just slow down. You really have to read. And if you gotta read out loud and talk to yourself, just go in a quiet room by yourself so no one thinks you're crazy, but it's okay. Because you gotta talk yourself into the answer to really understand it. A jet lands on an aircraft carrier at a speed of 140 miles per hour, which is approximately 63 meters per second. So visualize a jet landing on an aircraft carrier. That's like the looks like almost like a boat, right? Like a big old like thing, but it's to really hold like a jet, like it's to hold it. It's not like a traditional airport where it's like all the space. Like literally, it's like a I don't know how to describe like a plane flying on a crane, like a
Yeah,
plane.
that's why it was hard for me to try to imagine it because I don't understand.
That's what I'm saying. It's hard. Like you might have to look it up, but like sometimes with the physics problems, the first thing too you have to do is visualize what's going on so it can make sense. Like an aircraft, like it's literally like a plane landing on a plane. Would that be right to say it like that?
Like landing on a boat.
On a boat or like something like a boat. There we go. So like a plane landing on a boat. So it's flying in and it's going. So now think about it. First word, it's what? It's doing what? The jet is doing what? But what is it? What does it say?
It's landing. So
That's
it's
the
going
verb,
down.
right? It's landing. When you land, what does that really mean? You're coming to a
Stop.
stop. So now in the realm of physics, right? Is that plane getting faster or is it getting slower?
Slow.
Slower. So for it to get slower or slow down, it has to do what?
Decelerate.
Say it louder.
Decelerate.
Decelerate. But for you to decelerate, that means something has to be present. Which is that? If you need to decelerate, what's present? Acceleration is present. So now we can assume that there's an acceleration. We can assume there is acceleration because we're landing and we have to slow down. Now, what were we given? What were we given?
The speed,
The speed, which is what?
63 meters per second.
63 meters per second, right? 63 meters per second, right? So we got acceleration is present and we have a speed. What else did they give us? Time, because they give it to us in the next one, right? So now when they said, what is the acceleration? Assume constant. I never changed. I'm so sorry, y'all who are online. We are on this question. Can y'all see this online? Did I change it? Can you see it? All right, okay. All right. So we also now have a, who just said it? Someone just said it. We have a what? A time. We got a time too, right? Which is equal to what? 2 seconds, right? So we got a time. We know there's acceleration present, and we need to find our unknown. Now, for this first question, what is our unknown?
Zero.
What is our unknown?
Wait, I'm sure.
What are we trying to find? We're trying to find acceleration. They want to find acceleration. So we know from it landing and slowing down that it's present. So we know acceleration is not going to be equal to what?
Zero.
It's not going to be 0. So it's going to be some type of number, right? We have a velocity, right?
Velocity 0.
Hold on. We have a velocity. It's 63. Now let's look at this, right? Hold on. And we have a time. Now, is acceleration velocity over time?
Yeah.
Change in velocity over time. Stay with me. Hold on. Change in velocity over time. What is the change in velocity? It is the what? Read it in English. Change in velocity is equal to the, say it louder, final velocity minus the initial velocity. So let's think, right? You are landing, right? When you're landing, are you moving or are you at rest? In the beginning, you're moving, right? But your goal is to do what at the end?
Stop.
Rest or
Stop.
stop. So at the end, synonym for the end is also
Final.
final. So at my final velocity, I want to be 0 because I need to
Stop.
stop. So now I can assume that what? Exactly. So now when I assume that my final velocity is equal to 0, now I have something I can work with, right? Because now which kinematic equation can I use? Say it louder. The first one, because you could use a definitional equation up here, but we could also go right here and use this one. That's the beauty with kinematic equations. Say it louder. What are you saying?
I think I might have did this wrong because I did.
Let's see if you get the right answer, because then they'll show if you did it wrong. Now, I'm going to write my first kinematic equation I'm going to use, right? My final velocity is equal to my initial velocity plus my acceleration times time, right? Now let's think about it, right? We just said our initial velocity is equal to, sorry, we didn't say that. Our final velocity is going to be equal to what?
0.
0. I'll put it in blue, right? This is going to be equal to 0. Our acceleration is the unknown. I'll put it in green. But we do know our time, right? What is our time? 2 seconds. So I got 2 over here. And do we know our initial velocity? What is it? 63, because we're coming in hot at the beginning at 63 meters per second. Yo, this is crazy. I was just working with 7th graders and they literally had an equation just like this. This is a 2-step equation. It's just so funny because I was like, why are we doing this? And then to see it in physics later that day is crazy. So here's a 2-step equation. See and I do, right? I can't solve this right now because I have these 2 variables on the same side and I have a 0 right here. But I see positive 63, right? So what I do is I'm going to subtract 63 to move it to the other side. So now I have 63 over here, and I should still have my 2a, right? Now I have a 1-step equation. Now I see multiplication by 2, and I do division by 2. So now I divide this, right? And I still have it. It's negative, right? What's 63 divided by 2? Say it loud. I'm going to use our big voice in here because you're right. 31.5 meters per second squared. Because it is an acceleration. Now, acceleration is what? Quantum quantity, a scalar or a vector? Vector. So it has a what? Direction. Where is the direction in this answer?
The negative.
The negative. Let's think about it, right? I'm landing, so that means I need to stop, which means I have to, before then I slow down, which means we had somebody said it earlier, am I accelerating or decelerating? Decelerating would means I will be going, and my acceleration would be in the negative or opposite direction of my motion. So now that my acceleration is negative 31.5 meters per second squared, does that make sense in my goal of me trying to come to a stop? Yes. So now the math makes sense of logically what I think a jet would be doing on an aircraft carrier. So that's how you can also know that you did it right. It makes sense.
So is that acceleration is opposite of velocity or deceleration?
No. Don't try and generalize it. Just look at this right here. The acceleration in this situation right here is opposite of the motion that we're going in. Why is that? Because we're trying to slow down. The acceleration is opposite in the motion that we're going in because we're trying to slow down. But that's in general. That's in general. If I'm trying to slow down, my acceleration and my motion going 2 different ways. Opposite. If I'm trying to speed up, my acceleration, my motion going the same way. Slowing down, speeding up. Slowing down, speeding up. Slowing down, speeding up. Now, because we just did this, this is literally like a perfect leader, right? The next part of the question, what does it say? If the jet touches down at position X, right, equals 0, what is its final position? Now, we got to come back here, right? They don't give you much, but you have to think, what do I have? That's why we start off with our given. What did they give us? What was given to us? Which is what? 0. Okay. Their initial position, let's just say X is 0, right? What's its final position, right? So they want to find out the unknown is final position, right? This is initial position. We want to know what's the final position. Now let's think about it, right? If the initial position is 0, right? I'm gonna add another one over here, right? Displacement is equal to your initial position, your final position minus your initial position, right? If the initial position is equal to 0, then we can conclude that our final position is equal to our displacement, because technically this is 0, so now it'll just be the final is equal to displacement. So technically, we can assume that the final position is equal to the displacement, right? Now, what does that do for us? We can use which equation now to try and help us find this out. We have two options at this moment. Which two equations can we use to help us find out? 3 or 2, just because we're trying to find displacement. Now, which one we want to use? That depends on what else we have, unknown variables and known variables, right? Now, let's try and pull in some more variables, right? If this is the jet, right? Is this the same jet that we're talking about from the previous problem?
Yeah.
So if it's the same jet that we're talking about from the previous problem, what do we know about the jet? Describe its motion from what we just calculated. Down because it's doing what? It's decelerating, which means it has a what? Acceleration. Its velocity is changing, but it has an acceleration. Do we know what that acceleration is? So we have an acceleration and we know what it is. So we're assuming that it's the same acceleration that we just found, which is 31.5 meters per second squared in the negative direction. So if we assume that it's still moving the same direction with the same acceleration, what else can we assume?
It needs to be divided.
Same time. Same time. Exactly. Yes. Same time and same initial velocity. So now, therefore, between this finding displacement, right? Which one we use based off what we have? The second one or the third one?
Oh, no, I use the first, the third one.
The third one. We're going to use the third one. Why are we using the third one? Go ahead.
What is that?
Initial position. A lot of books that use X to represent position. But position and the change of position is just displacement. So if you have initial position and the final position, just the change in between them is your displacement. But I just gave you that right now to make it, because they put that XI right there. If you look in the textbook, it would just be like X all the time. So I just gave you that to help it make sense. But it's just the same concept. For me to say, what was I just saying? Now we use a third one, right? Because we have an acceleration, we have a time, and we have initial velocity. Now let's go back over here and let's just find this, because we already assumed that if we find this, we'll find our final position. That makes sense?
Say that again?
We have acceleration, we have a time, and we have initial velocity. So we have 1, 2, 3, and 3 again. So now all we gotta do is plug these in to find our displacement. Why do we want to find displacement? Because we already concluded that our displacement is going to be equal to our final position, because our initial position was 0. And displacement is equal to final position minus initial position. So if initial position is just 0, then our displacement really is just where we're at the final. So let's find our displacement. We're back here. BI delta T plus 1/2 A squared. Physics. How we just plug it in? This is 63. This is 2 seconds. 1/2. Negative 31.5 meters per second squared. 2 seconds squared. Plug all these in. The actual answer that you should get, I believe, is like 63. Yes. Physics, math, 63 meters. If you wrote lines 1, 2, 3, you would get full credit. And that's all you have to do. But this is the hard part. Look how we had to get 3 different variables from assumptions. Assuming that it's the same process. That's everything. That's what I said when we did the stat graphs, right? Assuming that all these things are happening at the same time. The acceleration is negative 31.5 meters per second squared. At the same time, the initial velocity is 63 meters per second, and then changing the final velocity to be 0. All of that is happening at the same time. But because we know all that's happening at the same time, then we're able to find out how far you're going.
So we're able to find out what,
How far you're going.
how far we went.
Yes. Any questions about that? All right. I can cover the last one very quickly. Just give me a second. I know the last one was a lot. Wow. Okay. Now, matter of fact, do you want me to stop here and start next class with the last one so I don't rush through it?
Yeah.
Okay. So let's do that, right? I'm going to stop right there, right? But that last one, now that we just did this, right? I want everybody to come back. I will grade that, yes. With the last one. Come back to the last one because it has 4 parts. Practice on the first 3, but come back one more time to do the last one and do it over again and take your time with it. Like, honestly, take your time with it. If you want to use a cheat sheet, that's fine. But really take your time with it and try and understand it, because I'll break down each part, because really it's literally just all the previous questions just asked again and again and again. And then in the last one, please notice that it's asking for, this one is worth 4 points because it's 2 questions that you have to answer. What is the final velocity and the position? So you have to use almost 2 kinematic equations, and I wrote it on there, right? So go over what I just wrote, what you took notes on from the first 3 questions, right? Then when you get to that 4th one, just give it an honest today is Wednesday, right? So you have a whole 5 days. When we come back on Monday, we'll actually come back in person and we'll actually probably sit down and do this on top of learning some more stuff. But I really want you to take this time in the weekend and really just make sure you at least try number 4 by yourself. What we just went over today. Find your given and do your assumptions and your unknowns, and then pick which kinematic equations. For this last one here, please use the kinematic equations as best as you can. Get comfortable with them. But try to do the kinematic equations. And then we'll come back on Monday and we'll go over it by step, and then go back into the forces stuff and make the connection. Sounds like a plan? All right. Same thing for everybody online. I'll post this when this is finished. I'll see you guys on Monday. We'll be in person on Monday.
All right, thank you.
No problem.
Professor, I sent you an email. This man just run out.